some definitions that need to that we need to get down. First of all, we have what's known as a scalar. Now, the root word of scalar is scale. A scalar is nothing more than a single real number. It indicates the magnitude or size of a quantity. Okay, so scalar is something that's singular. It indicates the magnitude or size. A vector, on the other hand, is a quantity that has both magnitude and direction. So there's a big difference. Scalar is one thing, magnitude or size. Vector is magnitude and direction. Okay. So what we're going to do is we're going to go ahead and look at a few examples, okay, as to if it's a scalar or a vector. So based on this definition, a scalar is a magnitude or size. Vector has to have both magnitude and direction. And when we're talking about magnitude, what would be another word for magnitude?
Bigness.
Yep, bigness, okay. How much something is. Okay, so let's go ahead and look at an example. We'll see how you do. If you don't know, I just want you to take a guess. Is this a vector or a scalar? A boat traveling at 15 miles per hour. So just take a guess. Is it a vector or a scalar? So what do we think it is? And the answer is scalar. Okay, the reason why it is a scalar, can somebody tell me why it is not a vector?
Because it doesn't have direction.
It doesn't have a direction. So, let's look at another one. A hiker walking at 25 paces due west.
I know this one.
Vector or a scalar?
Christina,
Vector, nice job. Okay.
you may have been slow, but you were accurate, so that's all that matters.
Is this vector or scalar a person's weight on a bathroom scale?
Christina. Christina. Christina, you take
Clicked it.
Who was the last one?
I'm writing down.
What?
A person's weight on a bathroom scale. You guys all thought that was scalar.
Oh, it's vector because it's that. Because it
The
obviously.
vector, yeah, because of gravity, the force of gravity is actually going to pull your weight down. So you are exerting a force downward. So that one actually is a tricky one.
She made that up.
No, I didn't make that up. Here we go. A parachutist traveling down at 12 miles per hour.
Christina, you better not be last. You are last again.
Vector, nice job.
Always last.
You really need about this one.
Okay, so now let's go ahead and talk a little bit about vectors. Here are the basics of a vector. A vector is denoted, so you can denote it three different ways. The first way is to denote it by its initial point and then its terminal point. Okay, so notice here we have an initial point. This is also called a tail. We have our terminal point, which is also called a tip. And so we can either name our vector by that, A, B. We can name it by vector A, which is a lowercase letter.
Is there just like half thing on the top?
Yeah, that's general. I always put an arrow. So if you want to go ahead and put an arrow, that's fine. But a lot of your vectors, they'll just have that single one there. Because the other way implies it's a ray. Okay, and so remember the geometric. It doesn't matter though to me. Or the other way you can name it is just by using a solid lowercase letter. So those are what the vectors look like. We have our initial point, our terminal point. Initial point always has to come first on the vector. Standard position is a vector with its initial point at the origin. So like the origin on a coordinate plane. The direction is the angle between the vector and the positive x-axis. That is what we call the direction. Biggest thing you need to get there is that it's the positive x-axis. And then the magnitude is the length of the vector denoted. It looks like absolute value symbols, but when we refer to vectors, those absolute value symbols symbolize magnitude. Okay, so it is not absolute value when we're talking about vectors. This is magnitude. So I'll let you get that down, and then we'll go ahead and look at a few example problems.
Oh,
We got some $2 Mars bowling shoes.
Yeah, they're
Little
awesome.
polos over the weekend.
They're green and yellow.
They wore them to our dance competition.
Matched.
Okay, so we're gonna go ahead and look at the next problem. Okay, so notice what it says. It says draw a diagram for each quantity. Draw a diagram for each quantity. So this is gonna be what the first part of your homework is gonna look like. So A is 20 feet per second at a bearing of 30 degrees. So what you're gonna do is you're just gonna go ahead and start. Oh, gotta use my pen first, sorry. Okay, so we're gonna go ahead and start with a initial point. Okay. So I could do this right here, 20 feet per second. Okay, that's one way. Okay, another way, and this is the way that you will see it done most often. Okay, whenever you see that 0, 3, 0, that means that you measure from the north direction. So you might see it written this way as well. And this would be 30 degrees, and this would be at 20 feet per second. So it all depends. You will use this second one like if we've got some word problems and that's what they tell you. This next one's 75 pounds of force at 140 degrees to the horizontal. Yeah, they're all different. Yep. So this next one, 75 pounds of force at 140 degrees to the horizontal. So here's your horizontal, right? Where will 140 degrees be? On the other side here. So there would be your force vector, and we're going to do 75 pounds. Last but not least, once again, this is a navigation problem. It says 30 miles per hour at a bearing of south 60 degrees west. So what that means is if you have 4 directions here, what usually symbolizes up? North, south, west, and east. So this is generally what you will see. Okay, when it says 30 miles per hour at a bearing of, what you're going to do here is you're going to start at the southerly direction. That's what this states. And you're going to go 60 degrees from the south here to the west. So that means I'm going to measure over 60 degrees right here, and that is where your vector goes. Okay, and that's going to be 30 miles per hour. Okay. So, and once again, that is used when we deal with navigation and surveying problems. So far, we've identified what a vector is, what a scalar is. We've went ahead and looked at how you draw in vectors. Now what we're going to go ahead and do is we're going to go ahead and look at this next problem, which talks about parallel, equivalent, and opposite vectors. Now real quick, I don't know if you necessarily need to write these down. Okay, first of all, parallel vectors have the same or opposite direction, but they do not have the same magnitude. So 2 vectors could be parallel. If you had one like this and another like this, those would be parallel vectors. Okay, another one, it could be this way. Those are parallel. Kind of the same definition of parallel lines. Equivalent vectors have the exact same magnitude and direction, so equivalent have to be identical. And then opposite vectors have the same magnitude but opposite directions. So something like this and this. So the magnitude is going to be identical, the directions are going to be opposite. And so we're going to now talk about what's known as the resultant. The resultant is what happens when you have 2 vectors and you put them together. You either add them or subtract them. And so there are 2 ways to find resultants, and so this is taken from your book. The first one's called the triangle method. The second one's called the parallelogram method. We're going to look at the triangular method, okay? And we could even look at the parallelogram method if you wanted. But the triangular method is called tip to tail. So you're going to start with the first vector. All right, you're going to take the second vector and you're just going to go ahead and place that on the tail of the other one, okay? Or actually, I said that wrong, so that the tail of B touches the tip of A. Okay, and then your resultant will be the one that's left. Now, where this comes into play, okay, where this comes into play is like when you have planes that are flying, they have a wind, okay, and the wind is going to come in and the wind is going to somehow alter their course a little bit. The wind's going to push them off course. Same way with a ship at sea, you're going to have your current that's going to probably push you off course a little bit. So you have what's known as the resultant vector. So let's go ahead and look at this. It says find the resultant vector. So I'm going to start with vector v. That is the very first vector I'm starting with. Okay. Now, in order to do the resultant, here's my v vector. I'm going to take vector w. Okay, just a second. There we go. I'm going to take vector w and I'm going to place it just like this. Now the resultant vector is going to start here and it's going to end here. Okay, that's what the resultant is. And so if I go ahead and draw that in, this is what I'm going to get. There is my resultant vector. And we call that v plus w. So that resultant vector is called v plus w. Questions? Pretty straightforward. Let's go ahead and look at this one. Draw a vector diagram of 3x minus 2y. So 3x minus 2y, so that means how many x's? 3. So I've got 1. Oh, wrong one. Ah! There we go. I've got 2 right here. And I've got 3 right here. So that's 3x right there. Now, what do you think the negative 2y means? Okay, because here's y, right? What do you think the negative's going to do? The negative's going to make it go the other way, like this. Okay. So now what I've got is I've got negative 2y. So if I have negative 2y, that's going to be 1y. What do you mean? How? Based on what you're given in the problem. Okay, so there is your negative 2y. I mean, because in the problem they're going to give you that these vectors look like this. So your resultant is going to be right here. So that will be what 3x minus 2y looks like. Now, if that would have been plus 2y, you would have been up here somewhere. You have to go with whatever you're given there. Okay, whatever the vectors are in the problem. Okay, so let's go ahead and look at this. It says Mitchell swims due east at a speed of 3.5 feet per second across a river directly toward the opposite bank. At the same time, the current of the river is carrying him due south at a rate of 2 feet per second. Find Mitchell's speed and direction relative to the shore. So you have a river here. Okay? And so what ends up happening is we have a person traveling across the river, and they're going due east, which is this direction right here. Okay? That's due east, and that's 3.5 feet per second. Unfortunately, what ends up happening is there is a current that carries him south at a rate of 2 feet per second. So here's the current, and this is at 2 feet per second. So what ends up happening is instead of traveling exactly due east, that current is actually going to shove him down a little bit. And so he's going to be traveling at a resultant of this right here. And so now, yeah, exactly. What we need to do is we need to find his resultant speed as well as the angle. And so as you've already heard Mason say, you're going to use SOHCAHTOA. You've got a right triangle right here. So to find how fast he's actually traveling, what am I going to use? Pythagorean theorem. So you've got 2 squared plus 3.5 squared. And that's going to equal his resultant. So you know 2 squared is 4. What's 3.5 squared? 3.5 squared, let's go. 3.5 squared. 12.25. So you've got 16.25. So to find the resultant, what are you going to do? Square root of that. What's the square root of 16.25?
4.029.
So 4.03 feet per second. So that's his resultant speed. Now we got to find the direction. Okay, so we've got to find this missing angle. So how can I find that missing angle? Tangent of that angle, we'll just call it theta, is going to equal 2 over 3.5. So go ahead and do the inverse tangent for me of that. Tell me what you get your angle to be. So what? 7.4? Did somebody else get 29.74? Okay, so that's what. So relative to the shore, okay, he's actually traveling a direction 29.74 degrees southeast. Okay, so let's see what we go ahead and have for our answers. Mitchell is swimming at a resultant velocity of 4.03 feet per second in a direction of 60.25 degrees southeast. Now they have theirs a little bit different. Okay, 60.25 is actually the opposite of that, so what makes would be the best way to say that. If you have this plus 90, it's the complement. So there are multiple ways you can say it based on the direction. So this would be correct as well. Okay, so understand that when you look in the book, depending on the direction you specify, you could have an answer that would be the complement of that. So anyway, questions? All right, so last thing we're going to talk about is rectangular components today. Rectangular components are exactly what we just got done looking at. It's your x and your y components. And so here's an example of the rectangular components. You have a person pulling a wagon at a force. You have a component of x and a component of y. You have a force of x and a force of y. And so what we're going to do is we're going to look at a question here. It says Harry is pushing the handle of a lawnmower with a force of 450 newtons at an angle of 56 degrees with the ground. Find the magnitude of the magnitudes of the horizontal and vertical components of the force. Okay, really easy. Because all I'm doing is I'm making a right triangle. Here's x. That's your horizontal. Here's y. That's your vertical. And so really when you think about this, we could have studied this when we did our SOHCAHTOA. How do you find x? Cosine 56 equals x over 450. Yep, sine of 56 will be y equals y over 450. So all you're going to do is you're going to take 450 times the cosine of 56. That'll be your x component. So what is that? What is 450 times the cosine of 56? Now be really careful that you're in degree mode. Not in it.
1.63 versus
Somebody else get 251.64? What'd you get for your sign?
373.
There you go.
1.7.
Okay, so here's your vertical component. Here's your horizontal component. That's it. That's all you have to do. Okay, pretty straightforward, pretty easy. I think I've got one more problem we're going to look at, and then we'll call it good for today. Okay, a player kicks a soccer ball so that it leaves the ground with a velocity of 44 feet per second with an angle of 33 degrees with the ground. Find the magnitude of the horizontal and vertical components of the velocity. So once again, we want to find x, we want to find y. So the easiest way to do that is to draw this in, okay, as a right triangle. So how do you find x? Yep, equals. Okay. How do you find y? So we can go ahead and solve these as we've already done this. For the x,
Yep.
what was it, 36.90? And what's the y? 33?
23.
Oh, 23. There you go. So there's your components. Pretty straightforward. The thing about vectors is we went through a lot of stuff today, but it is fairly easy, and I think you could should be able to handle it. So I need you to go to page 488 right now. 488. This is what I need you to do. I need you to do 1 through 6. All. I need you to do 8 through 18, the evens. Now real quick, okay, real quick, what I want you to do is as you look at 8, 9, and 10, or 8, 10, and 12, sorry, I said that wrong, you do not have to use a ruler, you do not have to use a protractor. Just do that like the examples we did in class. We've got a few more that we need you to do. I need you to do 28 through 34 of the evens. And then I also need you to do 42, 43, and 44. 42, 43, and 44. Now, we're going to move through this quickly, so I'm not going to probably give you a lot of days. So this, make sure you have it done for tomorrow.